Alright, so today we are solving applying derivatives to analyze functions, the unit test under the course calculus. So let's go. So let f be a twice differentiable function, and we have given a graph. Which of the labeled points are inflection points of f? Okay. In order for it to be the inflection points of f, we know that the graph must change concavity. So it must change from concave up to concave down, or vice versa, from concave down to concave up. So if we analyze this portion where the graph, changes concavity, it is the point C, as you can see here. So it didn't change the concavity right here, D, but it is changing at point C, and at point B it's just following the same pattern. It's not changing. So can we say that B is the point? No, it is definitely not the point. B and D is definitely not the point, because it isn't changing the concavity anyhow. It is changing the concavity at C for sure. For B, if you have a close look, is it changing the concavity? No, it is not. It only changed at D. At C. So C should be our correct answer. Yes. So moving on. So the derivative of function f is given by this function. Where does the graph of f have a relative minimum? Use a graphing calculator. So let's see. This is the f prime. So this is the function. Where does the graph of f have a relative minimum? So basically, where f prime is equal to 0, we have to note down this. Well, it is on this point and on this point. So for these 2 points, we have a stationary point, or f prime equals 0. Now we have to see where it is the relative minimum. In order to do so, we need the f double prime. Remember, this is f prime. So f double prime is just single prime for this Desmos graph, and we have to see which of them is negative. So how do we see that? We plug in these x values to the f double prime function and see which one gives us a value of. For minimum, we need a negative value. Sorry, positive value. Double prime have to be greater than 0. So it is the case with f1, which means x equals to 1 is our answer. There we go. Let f be a function defined for all real numbers except for 4, because if we plug in 4, the denominator becomes 0 and it's undefined. So let f prime, the derivative of f be defined as this, on which interval is f increasing. Basically, this is the same interval where f prime of x is positive, is greater than 0. Well, we don't have any. So the entire domain. So where f is increasing, where it is f increasing? We have to see the graph. Oh, here, if it is greater than 0, when it is, asymptote is where this line is asymptote. So as you can see, if we keep on increasing, it is going closer and closer to 5, but it's never touching 5. So 5 is the value actually. So here also, no, it's getting closer and closer to. Okay, I think it's 4. It's not 5, yeah. So from 4 to infinity, we have this function being greater than 0 or above the x-axis, and hence, because this is the, function for f prime. So if it's greater than 0, which means the function f is increasing. There we go. Okay, so the twice differentiable function h and its second derivative h double prime are graphed. Given that h prime c is equals to 0, so which means this is the h, and at this point is, the gradient is 0 because h prime gives us gradient. What is an appropriate calculus with justification for the fact that h has a relative minimum at x equals to c? Because the h double prime has a value at this point which is greater than 0, is a positive value. H is the lowest point that, no, yes, this is the one. And h double is increasing at x equals to c, no, this is not true. A is our answer. Because h double prime actually tells us if it is greater than 0, then this is minimum. If it is less than 0, then this is maximum. So this is the calculus-based justification we have. What is the absolute minimum value of f? Okay, absolute minimum value. In order to find minimum value, we have to differentiate the function, or in other words, find f prime x. And absolute minimum value of f can only be told, we can only say by analyzing the stationary points. Here we have 3 stationary points, and we have to see for which one we have a minimum, and that is where the f double prime comes. So we need 3 of these in order to check these 3 points. So we plug 1, 0, -2. We have to fix it right there and a bit of right there. So we need minimum, which means we need a positive value greater than 0. So does this give us a greater than 0? Okay, so we need absolute minimum. We have 2 minimums, 36 and 72. So now let's see which one gives us a great a value that is the minimum. So f36 gives us this. No, sorry, f1, not 36. 36 actually indicates that this is the minimum. So f1 is 0, and f of -2 is -27. So the absolute minimum is -27, as we just found. So function h is graphed. Select all intervals where we need the h prime to be greater than 0. Basically, the gradient should be positive. And h double prime to be less than 0 basically means concave down. It is concave down. Like this. Concave down. It's concave down basically means in the number line, this is 0, -1, 1. In the number line, if the gradient is moving towards the left, the magnitude of gradient is moving towards the left, then we can say that it is concave down, or h double prime x is less than 0. So let's first check out whether for this interval we have the gradient to be positive or not. So from -4.5, which is this value, up until -3, which is this value, as we move towards the left, it is going upwards. So this is not positive. So cross this out. From -4.5 up until 3. Because we're going to the left, it should have been gone downwards in order for the gradient to be positive, but it is not. So it's negative gradient. What about from -3 to -1? So from -3 to -1, as you can see, it's the same piece of function. I mean, it's the same portion. It's not changing anything. So from -3 to -1, as we go towards the left, it is going upwards. So it's a negative gradient. It's not true. What about -1 to +1? Yes, this is true. It is positive gradient, because from -1 to 1, if you go towards the right, it is going above. So this one is positive from -1 to 1. Okay, going to the right means above, so this is true. Now we have to check whether this is true or not. So what happens? What is the gradient actually doing? Basically, it is becoming more and more positive, right? It is 0 here, and as you can see, the gradient is becoming, the tangent to the line is becoming more and more steep. Hence it is becoming more positive. So it's going to the right actually. So this is true, but this is not true for this one. So our answer should be D in this case. Okay. So on which interval is the graph of f concave up? And again, for concave up, we need the f double prime. So f prime we need the f double prime. No, first we need the f double prime equals to 0. So we need the values, or we could just find the values for which f prime is equal to 0. So we have the f prime, and these are the function values for which f prime is 0. Now we have to see on which interval is the graph f concave up. Basically means f double prime. It basically means f double prime of x is greater than 0, concave up. So for what intervals do you have f double prime to be greater than 0? So we need f double prime of x, and this is x here. So we don't need this actually. So tell me, for what interval is it greater than 0? It's either towards the right side of 4 or towards the left of -1.5. So from negative infinity to -1.5 or 4 to positive infinity. This matches with our finding. So this is our answer. Alright, so the differentiable function h and derivative h prime are graphed. What is an appropriate calculus-based justification for the fact that h is decreasing? So how can we say that h is decreasing? Well, because the gradient is negative below x-axis. H prime is below x-axis, so less than 0. This is the appropriate calculus-based justification. H is negative? No, H prime is negative. H prime is increasing? Well, nope. H prime is negative is our answer. Let f be a polynomial function, and let f prime, its derivative, be defined as f prime like this. Okay. How many points does the graph of f have a relative maximum? Okay. We have the f prime. So this is the f prime, but it won't allow us to graph until we convert it to f. But we have to keep it in mind that this is f prime. So how many points does the graph of f, not f prime, have a relative maximum? It is the same as where, first of all, we need the points where the graph that has a gradient of 0. So basically, the gradient equals 0 is where the graph has stationary points. And now we have to see how many relative maximum. In order to find that, we need f double prime. Because this is f prime, so f double prime in this case would be just f prime. So now we have to plug these three values and see, because we want a maximum, we have to see how many gives us negative values, okay, for maximum. So for 3 we get, okay, so for 3 what do we get? We get negative value 1 maximum. For 0 we get 0, so it's not either maximum nor minimum. So we got 1 maximum point, and we only got 1 maximum point. There we go. Let f of x equals x times root over 4 minus x for x is less than 3. Where does f have critical points? Again, for f, in order to find the critical points of f, we need the f prime of x. So f prime of x will tell us where we have critical points, And to be specific, where f prime of x is equals to 0 is where, you know, f have critical points, and they have asked choose all x values that apply. So how many values do we have for which f prime of x is 0? It's just one value, which is 2.66. Now 2.66 is basically the same as 8 by 3, as we have just seen. So this is the only answer we could find. Okay, next question. An open-throated glass aquarium with a square base is designed to hold 32 cubic feet of water. So it's a square base, which means the base area is x squared if one side is x. So an open-throated glass aquarium with a square base is designed to hold 32 cubic feet of water. What is the minimum possible exterior surface of the aquarium? We don't know the height h, so let that be h. So this is the volume, the formula for volume. And we know that it is designed to hold VH square is equals to 32 because it is designed to hold 32 cubic feet of water. So this is h. And if we make h subject here, so 32 divided by x squared. So this is the height in terms of h. Now, the possible exterior surface area, so basically the surface area for the square base is x squared. And what about this? This is h times, h times x, x times h. So h times x. This is true for only one of these area, and we have 4 of these. 1, 2, 3, and 4. So we need 4 multiplied to that plus the base area, and it's an open-throated, so we don't have anything here. So this is the surface area, or the possible external surface area, and we want minimum of these. So we need, if this is surface area, let's say this is A, we want dA of dx, sorry. So in order to find this thing, we need an entire thing only in one variable. So we substitute h with, 4 times 32 by x squared, because we want to bring everything to a single variable. I can cancel this out. So you're left with x squared plus 4 into 32. What is 4 into 32? It's 128. So 4x squared plus 128 upon x. And we have to differentiate this thing. So x squared plus 128 divided by x. This is what we have got. X squared plus 128. Okay. So let this thing be a function of fx. And we need the differentiated functions, which is f prime of x. And because we need the minimum possible exterior area, we need this f prime to be 0. And we only have one, as you can see, one point for which this function, or f prime x, is 0, and that is where x equals to 4. What is the minimum possible exterior area? Well, that is when x equals to 4. But in order to find the, the minimum possible area, we actually have to plug in f4, which is 48. Now 48 would be the minimum possible exterior surface area. Okay, let g be a twice differentiable function, and let g of 7 equals -5, and g prime of 7 equals 0, and g double prime of 7 equals 0. Okay, what occurs in the graph of g at point 7, -5? So at the point 7, -5, we know the gradient is 0, and the g double prime of 7 is equal to 0. So we actually don't have enough information to tell. If this was positive or negative, this thing, we could have concluded. If this was positive, we could have concluded that, okay, so this is minimum. If this value was negative, we could have concluded this is maximum. But since this is 0, we need other pieces of information, the values for, that before 7, let's say 6.5, or after 7, 7.5. We have to see, we need those values in order to tell what is, what occurs in the graph of g at this point. So which we choose option C. Okay, so what is the absolute minimum value of f over the closed interval from -4 to 3? We can graph this, and we can restrict the interval from -4 to -3 by adding adding this interval right there. So as you can see, this graph actually doesn't help that much, because it's already pretty much that shape, unless you zoom out or something. Okay, anyway, so absolute minimum value over the closed interval from -4 to 3. So this is, as you can see, it's -53. So -53 is the absolute minimum value, because if we go downwards, then we cross the 3 and we have a closed interval including 3. So -53 is our answer. Okay, so at what values of x does the graph of f have a point of inflection? So again, we need the f prime x first of all in order to help us with telling where fx is equal to 0. So we have 2 points here for which f of x equals 0. And now we check f double prime x in order to see where, for what values of x does f have a point of inflection. So in order to have a point of inflection, we need f double prime x to be equal to 0, which is 1 point here. There we go. And what about f double prime 6? It is not equal to 0, so we only have 1 point, and that is when x equals to 0. X equals to 4, x equals to 4, it doesn't exist. And what about 6? No. So because f prime of x is only equal to 0 for 0 and 6, so 0 is our answer. Where does the function have a point of inflection? Okay, so I think f has no inflection. I'll explain why. No. X equals 0 and 4. Interesting. The second derivative is positive or negative. So we found the second derivative here. So for which f has a point of inflection. By looking for the interval where second derivative is positive or negative, the analysis is very similar to finding minimum and maximum points, only instead of analyzing it, we're analyzing blah blah. So we're analyzing f double prime. The second derivative of f is this thing, okay? F thing is equal to 0 for 0, or right. So f double, okay, yeah. So I analyzed where the f prime of x is equal to 0. Instead, we should have analyzed f double prime of x is equal to 0. It makes sense because point of inflection only happens where f double prime x is equal to 0. If f double prime x equals 0, this is where we have point of inflection, and it happens for 0 and 4. So 0 and 4 is our answer for this one. There we go. Okay, so let f of x equals this function. Below is Linus' attempt to write a formal justification of the fact that the equation f prime x equals to 2 by 3 has a solution between 0 to 9. So this is the function we have, and we need an interval from 0 to 9. So from 0 to 9, what values do you have? From the value of y, for 0, we have 0. We also have a 1 undefined value in the middle. We just saw it. Anyway, and we have a value of, let's say for 9, we have, what do we have? We have a value of 6. So Linus' attempt to write a formal justification of the fact that the equation f prime x equals 2 by 3 has a solution between 0 to 9, f prime of x equals f prime of x equals 2/3. So f prime of x is equal to 2/3. So y is equals to 2/3. Okay. between the interval. Justification. Linear. So linear justification. Okay, so we have to find the average rate. Okay, we have to find the average rate. So we have 0, 0 right there, and we have 9 right down. We have, for x equals to 9. What do we have? Okay, let's say we remove the restriction. We have 9, 6. Okay, so these are the 2 points, and if you want to find the gradient of this, so y2 minus y1, so 0 minus 6 is minus 6, and 0 minus 9 is minus 9, so it's a positive gradient of 6 by 9, y2 minus y1, so 6 is the y2 minus y1 is 9, so the gradient is 2/3. The average rate is 2/3, so there must be a single point in the, there must be a single point in the graph where the gradient is 2/3. So what she did was she checked out f0 and f9, so the average rate of change of f is 2/3, which is correct. We just found 2/3. So according to the mean value theorem, f prime x equals to 2/3 must have a solution somewhere in the. Yes, it seems to be complete. Lina didn't establish the average rate of change is equal. No, she did. Here it is. Lina established f is differentiable. Interesting. Nowhere it is mentioned that f is differentiable. It has to be differentiable between 0 and 9. Nowhere it is written, so we go with C. Okay, so let g of x equals this function, and let's see with a number that satisfies the mean value theorem for g on the interval from negative. We have -8 to -2, so we have this graph. And we actually need, okay, so we don't want to restrict. Instead, what we want to do is we have this graph, and we need x equals to -8. So x equals -8, and we also need x equals to -2. X equals -2. So we will get 2 values. So one is this, and one is this. So we have to find the value of c. First of all, we have 2 values. We have to find the gradient. So it's y2 minus y1. So y2 minus y1, x2 minus x1. It's 0. It is 0. And we could just tell that just by the -8 to -2, -8 to -2, y2 minus y1. It's 0. So we need g prime of x. We need g prime of x to be equal to 0. And this is what we just want to find, where we have g prime of x to be equal to 0. So the -6 and -2. We don't have -2 here. So basically they're saying that for -6, for -2 cannot be the answer because it has to be between 2 and 8, so 2 is not included, and that makes sense why -6 is the answer, because it has to be between -2 and -8, so that matches the answer. 2 more questions to go. Let g be a twice differentiable function. One of these graphs is the graph of g, and one of g prime, and one of g double prime. Choose the option that matches each function with its appropriate graph. Okay, let's start with this one and see, let's try and analyze the gradient. So we have a turning point, right? Okay, let's try from this portion. So we have a turning point right here. So most likely is the gradient is 0. So we need a 0 here. Do we have one? No, we don't. We do have one here. We do have a 0 here. So as we move right, it is going left. It is going down. So it's negative gradient. So the graph should be below negative gradient for this portion. This is true. And as we move towards the left, it should move downwards, so it is positive. And we can also confirm by this. If you move right, it is upwards. So for this portion, up until this portion, we have the graph should be above x-axis. So it is x-axis, above the x-axis. So this matches, correct. And this continues. It's positive up until this point where it is 0, and it makes sense because most likely here we have another turning point, and it continues to be up until this point where it takes the turn again. So yeah, basically not 2, it's the third graph. This one is 3. It's basically the gradient function for I. And the question is, where should be 2? 2 is here or 2 is here. So let's analyze the graph 2. Let's analyze the first one. Check whether this is correct or not. If it is correct, then 1 should be the differentiated function of 2. So we have, we have gradient 0 here because of the turning point. Do we have 0 here? We don't have 0 here. So it's, as you can see, it's between these two values, and we don't have 0 here, so 1 cannot be the answer. What about this graph? And this graph definitely can't be. So this means this is not true. Let's see whether 2 is a differentiation function of 3 or not. So if 2 is here, which means 2 is a differentiation function of 3. Let's analyze. So we have a 0 here, so we need a 0. We need a 0 here. Do we have a 0 here? We need a 0 here, and we do have a 0 here, so it matches. And if we go towards the right, it is below, so it's below. Yes, it is. And it is going above only after this point. So if you go right, it's above. So yeah, this is correct. This matches. If you go left, it is downward, so it's positive up until this point. So yes, it is positive up until this point. And if we go left, it is going up. It is negative up until this point. Yes, this matches. So our serial is 1, 3, 2. 1, 3, 2, 1, 3, 2, 1, 3, 2. So this should be our answer. There we go. The last question. Harold tried to find all the points on the graph given by this graph. Okay, we need all the points on the graph given by this equation, where the line tangent to the graph is horizontal. We need the line that is tangent to the graph horizontal. Basically means dy by dx equals to 0. So we need dy by dx equals to 0. First, okay, let's find the dy by dx. We need implicit differentiation here. So what do we have? We have x squared, x of, okay, what we can do is, no, we can't factor out y common here. We must do implicit differentiation. So this is a product rule. So x times, okay, we want to change the color. Okay, we're gonna cancel this out. There we go. So we need implicit differentiation, the product rule, u times v. So x times the differentiation of 2y, which is y squared, which is 2y times y prime. or dy by dx. dy by dx can be written as y prime. So we have x differentiation of y squared, which is 2y y prime, and then y squared differentiation of x, which is 1. So multiply by 1 is the same as writing and not writing. Then again we apply the product rule, x squared times the differentiation of y, which is y prime, plus y into differentiation of x squared, which is 2x, equals differentiation of is 0. So x squared differentiation of y, which is y prime, plus y times differentiation of x squared, which is 2x. Now what we do is we write 2xy y prime plus y squared negative x squared y prime positive 2xy equals 0. Positive 2xy equals 0. Negative x squared y prime. Sorry, this is also negative because we have a bracket here. Yeah, negative x squared y prime negative 2xy equals 0. We have positive y squared. Now what do? We take this term towards this side, so we have positive 2xy negative y squared. Okay, positive 2xy negative y squared, and we can factor out y prime here, so we get 2xy from here, and we get negative x squared. There we go. So y prime is basically 2xy negative y squared upon 2xy minus x squared. So does this match her results? Okay, we can factor out more. We can take y out from here, so we have 2x minus y. We can also take x from here, so we have 2y minus x. Because 2xy minus x squared and 2xy minus y squared. So y into 2x minus y, x into 2y minus x. Perfect. She's correct. Or he's correct. The student is correct. So Harold tried to find all the points on the graph given by this, where the line tangent to the graph is horizontal, so this gradient is equal to 0. If it is equal to 0, we have this is a mistake, because where the line tangent to the graph is horizontal, the gradient is equal to 0. If dy equals 0, how can this be 0 when this thing is 0? This is only possible when this thing is 0. And what they have done, they've made this thing as 0. So if this thing is 0 and this thing is not 0, this is undefined. Denominator can't be 0. Okay? Because if the denominator is 0, we have undefined. In fact, this thing has to be 0 in order to dy by dx to be 0. But here they have said this thing is not equal to 0. So mistake is in step 2. Okay, and we don't have to even go beyond because we know that step 2 is incorrect. There we go, and that marks the end of this unit test.